Go. Got to get this on the internet or it doesn't count, right? It's like it never happened. So that was a joke. Yeah, back when like classes used to happen and there was no record of them, they just like disappeared into the ether. That hasn't been the case for my classes in almost a decade. I've been recording classes for a very long time. At first, it was on a wireless microphone that I would wear around my neck, and I had MP3 files. And then we had software that captured the screen at the same time, and that was the coolest part. So now it's YouTube. But anywho, can you all see my M plus output in front of me here? Okay, so here's what I wanted to show you in case you've never seen this trick before. So you can take this output, let's say let's copy this much, and you could paste it into a Word document, but that would look sort of shitty, right? We don't want it to look shitty. We want it to look nice. So what you can do is paste it into Excel, and when you do, it will look like this. Now, it doesn't have to. Move this silly thing out of the way. Under data, there is an option called text to columns. Have you seen this option before? A few, not everybody. Okay, so those of you who have not, you're going to love this. I'm going to highlight the column and I'm going to hit text to columns. And then it says, oh, it looks like this is a table. And I hit next and it's like, do you want those columns to look like that? And I say, why, yes, thank you. And now it's in columns. So for instance, this right here, that is a terrible label. That is not a good label for a table. But you know what would be a better label? Something like loadings, since that's what I'm looking at, right? And then the next section, intercepts is okay. I can leave that alone. And then you can add, this is an estimate, this is a standard error, and I don't need these two columns. So I'll get rid of those. And last but not least, this still looks kind of shitty because of the differences in the decimals. So I'm going to highlight those columns, go back over to home, and format them as numbers. So now they all have the same alignment. So yes, I'm sure there's ways to do this in code in other programs, but if you want to do it the fast and easy way, you can use Excel to make your tables look nice. I often paste my tables from Excel into Word as an object. That way Word doesn't screw up my formatting. So whatever it takes to make your tables look halfway decent, my hope for you is that it should not take much effort to put a table in the manuscript or in your reports. Tables help me make sure that your model has been properly specified. So for instance, if I see this happen, item 1 has a loading of 1 with a standard error of 0. What does that tell me? Any guesses? If I see that in your results. Z-scored one option, the opposite. It tells me that item 1's loading was held to 1, which means that if you also held the variance to 1, your model is wrong. Because you either hold the factor variance to 1, which is what I instructed you to do, or you hold one of the loadings to 1, but not both. So if I see this, for instance, that's a giveaway that something went wrong in your code. So tables of parameters help me know whether or not you specified things correctly. And if you have questions about your code, you can always include that as part of your assignment. You can upload those files or just paste it into your document. That's fine too. Okay, so any other homework questions while we're on the topic as you're working through your own analyses? Think of it this way. You're all getting free statistical consulting. I would charge other people a lot of money for the privilege of looking at their analyses and telling them if they did something right, and you get it for free. Other than the tuition you're paying, right? Other than that, right? It's free. But so I'm looking forward to learning about your projects, and for some of you, you get a chance to be the first to look at the factor structures of your instruments. So that will be exciting to see what happens. Another question's busy chat window today. So if we have two dimensions, but they're both less than 6 items, we combine them into one factor since we want it to be testable. No. If you are one of the folks who has factors that have fewer than 6 items, and so I asked you to get 2 factors, your model should still have 2 factors in it. By having both factors in the model at the same time, your model will be both identified and testable. It doesn't mean that you have to pretend that it's 1 factor, though. You can still have 2. Just test them all at the same time. All right. Okay. Other questions? All right. Then let me get rid of Excel and we'll go to this. Quiz questions. So I had a chance to read all of your answers. For the most part, this first question went very well. There was some heterogeneity in some of the others. But question number 1, in considering global fit provided in CFA, what does the model chi-square tell you? And most of you correctly answered. It tells you how far off from perfect. So it is the discrepancy between the covariance matrix that your model predicts and what it actually is in the data. So the goal is that your model is not worse, that its height in terms of log likelihood is not significantly lower than the height of the perfect model. And you get a chi-square for the differences in height, where significance is bad because it means your model doesn't fit. 2 different classes of fit indices, SRMR, standardized root mean residual, I think, and RMSEA, root mean, I don't even know this off the top of my head. Isn't that sad? Root, no, there's an error of approximation. I know that one. RMSEA and SRMR are both indices that are relative to the same perfect H1 saturated model. So they are judging how much worse your model is than perfect, where 0 means that your model is perfect and anything greater than 0 is bad, and you want this to be in the neighborhood of 0.06 or less for what is a good model. CFI and TLI are different. They are testing your model against a comparison model that is the worst model, what is known as the null model, and it has no covariances in it. So the null model lets each indicator have its own mean and its own variance, but it has no covariances. So then those indicate, relative to the worst model, how much better is yours, where the best it can be is 1 for CFI, and TLI actually can go above 1, but you want bigger is better, above 0.9 or 0.95 for those. So it is the case that they can disagree because they're telling you the same thing from different perspectives. How much worse is it than best versus how much better is it than worst? And a few of you noted that these things can be subject to concerns about reliability. In general, the less reliable your indicators are, the smaller the standardized loadings, the easier it is for these things to look like they fit well. So if you have really strong indicators, it makes it easier to see that you have misfit. It's more blatant. If you don't have strong indicators, then even a wrong model can look not so bad because there's not a lot of signal there to work with. So questions or comments on that one? All right, move on. Local fit. So most of you pointed out that we should be looking at normalized residuals, but not a lot of you said what those are. So the idea of local fit is taking a deep dive into the model predicted covariance matrix and how it compares to the data covariance matrix, and the difference, the discrepancy of each of those possible covariances is what the local fit is looking at. And the normalized residuals standardize that discrepancy into something that looks like a z-score, where you want to look at relatively large values as indicating that those are the most important sources of misfit. So a few of you noted something about the loadings with respect to this. This doesn't have anything to do with the loadings. You can have local misfit whether your indicators are good or bad. Local misfit has to do with how well the model has captured how your indicators relate to each other. So if you have a 1-factor model, for instance, and it really should be a 2-factor model, then the items that actually should have been on the 2nd factor are going to have positive normalized residuals because they're going to be more related than what a 1-factor model would say. And the items that want to be on different factors are likely to be less related than what a one-factor model would say. So it's about the discrepancy between what the model says and the data says, given the model that you fit. It doesn't necessarily mean that your items are good or bad. That's what the loadings tell you. So it's a separate set of considerations. Several of you mentioned modification indices. So modification indices are suggestions based on the standardized residuals or the normalized residuals as to what you should do about them. And modification indices, as I call them voodoo, because they are theoretically impoverished just based on the math. How would your model fit better? And they will suggest things that make no sense. They will suggest error covariances, and if you have a model that has more than one factor, they will also suggest cross-loadings. But they will never suggest a new model. You will never see them say, you know what, you should fit a two-factor model instead, where these items go here and these items go there. Or you should fit a bi-factor model where you capture all of the extra residual correlations into a factor that makes more sense than having a whole bunch of error correlations. Like it will never say that. And so that's your job as the analyst to try and put a higher order picture on the patterns of misfit and see if there's a way that you can address them that would be more defensible theoretically by factors. So yeah, positive residuals mean that your items are more related than what the model says. Negative residuals mean that they are less related. So questions on that one? All right, last one, omega versus alpha. Both of them assume unidimensionality. Confirmatory factor models give us a way to say whether or not that assumption is reasonable. The differences from there, alpha assumes that the loadings are all the same. Omega lets them be different. So if you fit a model in which the loadings were all the same, what's known as a tau equivalent model, or what's going to be called a Roche model for the next few weeks, then alpha and omega would be the same so long as there are no error covariances. That's the third part. So omega has a place in the formula in the denominator for error covariances to go. So violations of local independence from a strict point of view, you can still accommodate with omega and you can't with alpha. But yes, if you fit a single factor model with no error covariances and you constrain the loadings to be equal, then alpha and omega are the same thing. In practice, to the extent that you have a single factor model that fits well, the differences between alpha and omega are usually pretty small, like second decimal place. They show up more so in models where the dimensionality is suspect. All right, and you need one per factor. That's the other thing. All right, I think that's everything I wanted to say about that. Any questions? Okay, if not, ugh, we don't want to go with this yet, do we? There, have a nice picture. We'll stare at a nice pretty picture instead, right? Let's see, am I sharing my screen yet? No. Well, why did you tell me that? Come on, folks. There you go. Now you can see my pretty picture, right? Oh, goodness. Is it working? I can't tell. All right. No, I was sharing it before, right? Or was I? Yes. Okay, good.
Yeah.
It's when the controls disappear, I can't tell. So, and then it's hard to get them to come back, but there's this very weird green bar that says I'm sharing. Okay. And then the last class, some of them couldn't see it for no apparent reason. So apparently Zoom is just having issues today, but we're good, right? You can see the mountain thing? Okay, so we'll look at the mountain thing while I ask you, what do you remember from last time? I'm watching the chat window, or you can make gestures, or you can talk. Logits transform the outcome. Yes. What else? IRT and IFA is just logistic or probit regression instead of linear regression. Yep. With a latent predictor instead of an observed predictor. That's the difference between those traditional regression models. Yep, yep. Factor equals theta. Yes, indeed. It's got a new name. It's got a new symbol. It's the same damn thing. The logit, yes. Here, I've got my conductor stick with me today, so we can all say it together. Ready? A logit is the log of the odds of the probability of a 1. This is more effective in person, but we got to make it work, right? Yes, that's one of those things to commit to memory. What is a logit? The log of the odds of the probability of a 1, indeed. And normal versus logistic, yeah, so instead of logit, you might have a probit. That corresponds to the z-score with that probability. So if you have the probability of a 1, you can find the corresponding z-score for the area to the left of that point. That's a probit. A better question behind those is why? That's a valid question, right? Why am I telling you about logits and probits? Because that's the magical way. Yes, gestures. Jing, do you want to give me that? Anyone else? Yeah, we want the logistic curve, right? Here. Yeah. I can't quite do it. Don't have the arms, but yes. The idea is to keep the outcome in bounds. So we can't predict probability directly with a linear slope. So where we want to get to eventually is the same idea in CFA, where we want to have a linear slope for the trait as the predictor, predicting each item response. The problem with binary and ordinal data is that the item responses are bounded. The probability of a 1 can't go past 1 and it can't go lower than 0. So we need a linear slope that shuts off as it gets up to 1 or down to 0. Logits and probits are the magical way by which that happens. The reason to use them is that we can specify the linear slope as predicting the logit instead. So it is a nonlinear transformation of the outcome to be predicted. We can predict a logit. The logit could start at 0. That would correspond to a probability of 50-50. And for a 1 unit change in the factor, the logit could go to 1, to 2, to 3, to 4, to 5. The logit can go on forever and ever. The logit has no bounds. But if I back translate the logit into probability, increasingly large logits still stay under a probability of 1. And there is a picture that goes with this, rather than me making silly hand gestures. Here's slide 8. Here's one of the pictures, mapping logits to probability. So the logits on the x-axis, you can have a linear slope that predicts the logit outcome because the logit can keep going forever and ever, and it corresponds to a probability that it is increasingly close to 1 or 0, but never quite gets there. And I like this one actually a little bit better. This is slide 9. So probability is on the top. So a 1 unit change in logit corresponds to a different interval of change in probability depending where you are. So if I start at a logit of 0, a logit of 0 corresponds to a 50-50 probability. If I go from a logit of 0 to 1, that translates into a probability of 0.73. So that's a big jump. If I go a similar unit change in logits from 1 to 2, that corresponds to a much smaller change in probability, and the changes that correspond to equal logits get increasingly smaller in probabilities. So the logit can be predicted by a regular old linear model. The predicted logits from that model can get back translated into probabilities that stay within their boundaries. And this is exactly the same thing as logistic regression, ordinal regression, probit regression, all that stuff that works with observed variables, which is why I feel like it's helpful to understand that connection, because our factors are the predictors, they're just latent. but it's still regression. All right. I heard something. Is someone going to talk to me? I get so lonely in my basement. Okay. Does that help folks who had questions about logits and why? It's just a trick. It's just a way to make sure that the linear model of how the factor predicts the outcome doesn't create outcomes that can't exist. We have it predict logits or probits instead, which keeps the probability bounded between 0 and 1. Right. Other questions or things you want to review from last time? All right, you want to talk about IRT then? Yay! So IRT models are completely differently looking. They look like nothing you will have seen before unless you've taken an IRT class. And the names that they use are so unimaginative, it's going to be hilarious. It's like its own world here. So let me get some of my windows closed so I'm not going crazy. Don't need that. I need this. So we're picking up on slide 22 of lecture 5. So I imagine that some of you have had IRT models before. How many of you? Can I get a show of hands or votes? 1, 2, 3, 4. Okay, so, but it's in the context of education, right? So this is the same models that you've heard about before, but in a different context. Attitudinal items that are more common in the social sciences like psychology, sociology, political science, and stuff like that. So some of it may still be new if you're thinking about it from a different perspective, because theta in these slides is not ability. Theta is a latent trait. It could be anything. Ability is just one type of trait that you could measure. But one's propensity to feel a certain way or do a certain thing or subscribe to certain beliefs, like those are equally valuable thetas that these models can address. So we're going to talk about, and I kid you not, this is what they're called: a 1-parameter model, a 2-parameter model, a 3-parameter model, and a 4-parameter model, because we couldn't come up with anything more interesting to name them. So here's your first one. And for all of these, I'm going to give you both versions in terms of what the predicted outcome is, the logit that corresponds to a linear model, or the probability that corresponds to a nonlinear model. And so this is our first one. This is what is known as a 1PL, 1-parameter logistic model. It is used to predict binary item responses from a single continuous trait. So we have our friend the logit here. That's this term to the left of the equal sign. The log of this thing in the brackets, that's the odds of the probability of a 1, equals this little thing here. This is our new friend theta. It's a Greek letter. Each subject gets a theta. And now check this shit out. Minus. A minus sign. When was the last time that you saw a regression model where it was phrased with a minus sign? Not unless the estimated slope was negative, but minus something. That right there makes this different. Minus what? The letter B. B has an I subscript because each item gets it. This thing is known as item difficulty. And here is why it's a minus sign, because difficulty is actually going the right way. Items with higher B values are more difficult, meaning people are less likely to get them right. So in all of the models we've had up to this point, difficulty was an item mean or an item intercept, where the direction was conceptually backwards. Now it's the right way. You can't tell it from this notation, but I also want to point out how these things are treated is different. B is treated as a fixed effect, meaning that as part of the estimation process, each item is going to get its own B value, an estimate, and a standard error that goes with it. So I get one for item 1, I get one for item 2, I get one from item 3, and the inference is constrained just to that item. Like, this is the difficulty of this item, and if I swapped out a new item, I wouldn't know what its difficulty is because each difficulty is item specific. That is a fixed effect. Theta, on the other hand, is a random effect. Even though we can ask for a predicted theta for each person, that's not a model parameter. What goes into the model is the variance of theta instead. So it is exactly the same as in CFA in that we don't need to know what the factor score is for each person. We pay attention to their means, variances, and covariances. Same story on theta. We don't need to know what theta is for each person because it's not a model parameter. We pay attention to the distribution of theta, which is supposed to be normal. If you want to predict probability directly, this same model looks like this. So it's e to what the logit predicts over 1 plus e to what the logit predicts. And I don't know why one of these is in italics, but the other isn't. So the difficulty is a location parameter, and it has a very specific definition. And I like this definition very much because it gives you a sense, I think, of where the item's located in a way that the other models don't. The definition of item difficulty is that it is the trait level needed to obtain a 50% probability of getting a 1. So it's how much trait do you need to answer this item well. And so if you are somebody who has a lot of this trait, whatever it is, and you encounter an item that has less difficulty, the logit is positive, which means the probability of a 1 is greater than 50-50. If you encounter an item that is located further than you are, so an item that has more difficulty than you have trait, that creates a logit that's negative and corresponds to a probability that is less than 50-50. So the one parameter, by the way, that is in the name is the B. Theta for each subject is going to be in all the models, and it doesn't get counted for whatever reason. Yeah, I know. It's actually a 2-parameter model, right? But that's not what they call it. And this is the logistic version of the model because we're using a logit link. If we were using a probit link instead, this would be called an ogive, normal ogive model. But it just changes the nonlinear outcome to be predicted. This part is the same, the theta and the B. So these difficulties, like I said, help you make sense of what the items imply for the location of the trait without necessarily needing to know how everybody else did. So for instance, if Huey came home, my 5-year-old, and he told me, Mommy, I got a 12. I'd say, good? Because I'd say he sounds excited, maybe 12 is good, but I'd have to ask some more questions to understand what 12 means. And if he told me, Mommy, I'm in the 90th percentile, because 5-year-olds tend to say those things, I'd say, great, buddy, thanks for helping me understand what the hell a 12 is. But if a 12 put him into the 10th percentile, then 12 is not good. So I have to have this additional information to sort of clarify what a given score means. And you don't have to have that additional information if you have people and items sharing the same metric, which is called conjoint scaling. So let me give you an example, not from education. This is an example from my own personal area of expertise. So you know the game Trivial Pursuit? Okay, so the game Trivial Pursuit, you have to answer questions. I am terrible at that game. I know nothing about history, geography, politics, science, nature, literature, sports, or any of the other categories. You do not want me on your team. But if I am playing a specific 80s pop culture trivia game, then I rule. I will run the table and take no prisoners. So this is from my personal area of expertise. This is a latent continuum of 80s pop culture knowledge. And on the person side, I have prototypical examples of people I would expect to be at various levels of this trait. And on the item side, I have questions that I think they would have at least a 50-50 shot at getting right. Would you like to play? Okay, I know most of you weren't alive in the 80s, so this may be a little bit out of your reach, but I can't bring myself to update my references to the 90s because I don't have that kind of trait knowledge for the 90s. I can't be the prototype. But for instance, if I were to ask you to complete these song lyrics, "Oh, Mickey, you're so fine, you blow my mind. Hey, Mickey!" Yes, everyone knows this song. It's Tony Basil, who's like 45 in the video, dressed as a cheerleader singing this song. My mom knows that song, right? My mom has very little 80s pop culture knowledge. She was raising kids and working full time, but I bet she would know that song. So I kind of put those two as equal pairing. I would say your average adult, somebody my age or older, could name all of the Cosby kids. Now, no fair using the internet. Would you like to play? How many Cosby kids can we name? Let's do this. I'm watching the chat window, or you can participate. So the youngest Cosby kid, Keisha Knight Pulliam, I believe is the actress's name. Come on. No one's playing. I know none of these. Okay, so as I said, people my age or older, which most of you aren't. Oh, Megan for the win. Rudy. Yes, Rudy is the youngest. The next one is Vanessa. And then we had Theo. And then there was Lisa Bonet, who was, I'm blanking on it. Oh my goodness. Denise, thank you. And then Sandra. Those were the original Cosby kids. And then they invited, what's her face? A very cute little Olivia was Denise's daughter when the show jumped the shark and they had to invent a cuter kid to bring in. Like that's a popular thing. But yes, the Cosby kids would be my example of a more difficult item for this, but not super difficult. I would say your average undergraduate would be familiar with the character Ducky from the John Hughes movie Pretty in Pink. Do you guys know who Ducky is? John Cryer. Yeah, you should see it. So ask the Google or the Netflix or the YouTube or wherever you get free movies from to watch Pretty in Pink. And Ducky is like the prototypical best friend who's in love with the girl and she doesn't love him back, and it's like a thing, but he's so adorable. Ducky, he was the man. My own brother one time thought he could stump me. He was incorrect, of course. He thought he could stump me. Who is the other guy besides George Michael who sang in Wham? Yeah, his name was Andrew Ridgeley. He did not go on to have a good solo career, from what I understand. Otherwise, you would know that. And then at the top, I would say the TV show Alf, which was circa 1987. Where was he from? No idea. See, this is a high theta question. This is a high item difficulty question. It's Melmac. Alf was from the planet Melmac. See, this is all this information that's floating up here that does me absolutely no good except for once every 2 years when I teach this class, and I can share my knowledge of useless 80s trivia with you guys. But the one thing I want to point out in this example, even if you don't answer any of these questions correctly, are there any numbers on this slide? I don't have a 12 here or a 0 or a 1 because I don't need them. The idea of item difficulty is that it corresponds directly to a trait level. In order to be able to quantify the trait level, I need some numbers, but I don't need the numbers to interpret what it means. And spoiler alert, we're going to set the metric of the trait the exact same way we did it in CFA by fixing the trait mean to 0 and the trait variance to 1. It's going to be called anchoring in IRT instead of identification, but it is the same idea. So once we fix the mean and variance of theta, then all of the locations of these items relative to that fall into place. I could fix the mean to be 10 and the variance to be 100 if I want. It doesn't matter. But so long as we nail something down, everything else arranges itself relative to that reference point. All right. How are we doing? Okay. So here's some pictures from Susan Embrinson's book that I liked. She's trying to make these points about scale scores and how you need to know how everyone else did in a given sample or population norms to be able to interpret them. This is an example from her book. We're looking at activities of daily living in older adults. And so these are things that one needs to be able to do independently to continue to live by oneself. And so she has fictitious older adults here located on the same trait as items of comparable difficulty. So look at the items on the bottom. At the easiest end is things like making sure you can control your bowels and your bladder, and then getting up, and then taking care of your, toileting and whatnot, dressing, all the way up to being able to go up and down stairs. And so the result of this process is that if you ask for the predicted trait level for each person, you can then predict whether or not they would be able to do each of these items. So the person with the most ability in her example, Vera, her ability places her at the same location as an item that's for tub transfer. So that means that she has a 50-50 probability given the model of being able to do this. Going up and down stairs is an item of greater difficulty, so that we know that she has less than a 50-50 probability. But for any item on the left side here, where her trait exceeds the difficulty, then she has a greater than 50-50 chance of being able to do that item. And the model will tell you exactly what the probability is of her at her trait level being able to do an item of any level of difficulty. So we can make inferences about items that weren't necessarily even given to her if we know where they are on the same continuum with respect to their location, which is their difficulty. So that's the cool thing about this, is that we can predict how someone would respond to an item that they didn't even take. Because all we have to know is the item's difficulty and their ability level, their trait level, and we would be able to figure out what would happen. So we can compare trait estimates from people who didn't even take the same test. One catch to this wonderful separation of items and persons relies on standard errors. In order to locate exactly where an item is with respect to its difficulty, we have to have enough people at that same place to be able to nail down exactly where it is. If we have an item, say, that's really, really difficult, people would have to have a really high level of the trait to be able to get it right. We need to have a lot of really, really high people to nail down exactly how difficult it is. Otherwise, it's hard to tell, and that would show up as a standard error that's relatively large. So the standard errors for these things do depend on the quantities of the sample. The parameter estimates themselves do not. So here is another version of this model that has a constant in it. And by the way, this one parameter model is also known as a Roche model. And the idea of what this is missing is starting to peek out with this letter here. So this thing right here, this A, it doesn't have a subscript, but it indicates a slope. So the difference between theta and difficulty is multiplied by something. So another way of phrasing this model is that we're saying that the slope that describes the relationship between these things is equal across items. We can see what what the model predicts given this constraint in this picture right here. So this is slide 30. So on the y-axis is the probability of a 1, which is the mean that we're trying to predict in this model. And on the x-axis is the person's latent trait. And if I identify the trait such that the mean is 0 and the variance of 1 is 1, then the x-axis is showing plus or minus like 3 standard deviations of the trait. I have curves here for 4 different kinds of items. These curves have a special name. They are called item characteristic curves, or ICCs for short, not to be confused with ICCs from my other classes, which means intraclass correlation. These are a different ICC, and they illustrate the relationship between the trait and the probability of a 1. So the first thing I want you to notice, these are nonlinear curves, right? They understand that at some point, more trait can't predict a probability that exceeds 1. So these curves asymptote up to a probability of 1, but they never cross. And likewise, they asymptote down to a lower probability of 0, but they never cross. These are generated from a model that's actually linear in the logit. And now I understand what the hell Susan was talking about. So we have a linear model if it predicts the logit. That same model, when back translating the predictions into probability, creates curves that look like this. So the point on each of these curves where the curve crosses a probability of 0.5, if we take that straight down to the x-axis, that is the item's difficulty level. So the location of item 1 here is -2. That means somebody with a theta of -2 has a 50-50 shot at getting this item right. And somebody, say, with a theta of -1 has looks like to be about an 85% chance of getting it right, and so on. The pink line has a difficulty of -1, so that's the amount of trait needed to cross the 50-50 mark. The blue line has a difficulty of 0, and the green line has a difficulty of 1. So these items differ in one parameter, their shift point on the x-axis, as their difficulty, the location. But the curves all have parallel slopes. That's the Roche model. So what did we learn about slopes in the context of CFA? What do slopes tell you? Discrimination. How related to the trait they are. Yeah, slopes are factor loadings, right? So those used to be important. So this model right now has a very strict assumption that all items have equal slopes. All items have equal discrimination. All items are equally good at measuring the trait at the difficulty location. So whether or not each item should have a different slope, we just learned is a testable hypothesis, right? Remember we did that in homework? You constrained the loadings to be equal and saw how much worse it made the model. This! Whether or not the Roche model holds, whether or not the 1PL fits, whether or not the items have equal slopes, that's a likelihood ratio test. That's a comparison of fit. The reason that Roche people, and I do say that like it's sort of a group of people with a very strong philosophical viewpoint, they like this model because of this property of specific objectivity. These lines are never going to cross. So the ordering of items stays constant no matter where you are on the trait. So for instance, the dark blue item is always the easiest, meaning no matter where you are on the x-axis, the probability of getting the dark blue line right, the probability of a 1, is the highest. Blue is always higher than pink, is always higher than light blue, is always higher than green. When you allow different slopes, they cross. And the ordering of items with respect to their difficulty can change at different levels of theta. And to Roche people, that is just not acceptable. To me, that's a testable hypothesis and probably not likely to be true. But isn't that just life? Yes. And here's where context matters, folks. If you have a math test, right? If Huey's in math class next year and he's learning how to add 3 plus 4 and 1 plus 2 and 6 plus 0, now arguably some of those items are harder than others, but they probably function equally well in measuring addition. Now think about the items in your homeworks. Andrea's shaking her head. Nope. Do you think they're all equally good? Nope. So yeah, to me, it's like, well, let's just test it and move on. And to other folks, that is not acceptable. It's not acceptable to let the slopes differ. So what would happen from a Roche perspective is that if you found an item whose slope wanted to be not like the others, you would throw it away. Like the world that I grew up in is you have your data and you try a model and see if it fits. And if it doesn't look like it fits, you try a different model and see if that fits. And you keep trying different models until you figure out like what the right model is. And that's your final model and you write it up and turn it in. From a Roche perspective, no, there is only one model. It's the Roche model. And so you just refine your data. You throw out people and items that do not fit the model until you get it right. It is a different philosophy. It's not one that I share, but that's in certain contexts, the benefits of a Roche model outweigh the costs if you are willing to throw away items and people to make it a plausible model.
Why would the slopes not match, I guess, in the scenario if they're supposed to be kind of constant throughout? I guess I'm a little confused about the Roche model.
So why should they, when would they not match?
Yeah, because you said they'll throw items out if the slope doesn't match what they're expecting.
To match the other slopes
Other slopes of what?
of the other items.
Okay, so when would they not match?
If an item is, say, shitty, right? Like if it's like if you think about this picture, an item that is unrelated to the trait, what would its slope look like?
Negative, right?
Negative or flat, right? Unrelated would be flat. Related the wrong way would be negative.
Okay.
And so arguably throwing out that item is a good thing. But what if you have an item that is related to the trait but just less steeply? Or more steeply for that matter. From my perspective, you should just let it have its own slope and move along. From a Roche perspective, that is not acceptable.
Why do they do that? Is it supposed to make it easier? Or I guess, is that for like, I don't know, make it equating and scaling purposes or something?
I have the same question about why this would even ever be useful. Yeah.
You can look it up on the internet. There's a Roche.org measurement group that talks about the beauty of the Roche model. Some of it has to do with equating and linking things because if the Roche model fits, then the sum score is a sufficient statistic for theta. And so that property is useful in a lot of contexts. Another is that an implication of a model with a different slope is that certain items count more than others. And so you could be in a situation, let's think of it in an educational context, where one student, gets 12 items right and another student gets 13 items right, but yet the student who has 12 items right could have a higher theta. Because if they got items right that counted more, then that would show up as a higher trait estimate. And do you want to explain to Johnny and Susie's parents why Johnny got fewer items right, but yet he got a higher score? Do you want to explain that? They don't want to explain that. So there's a face validity aspect of it too, that having items that differ in their parameters gets trickier. And I think that's more of a concern in educational settings than it would be in social science settings where we're more accustomed to just letting the slopes be different.
If there's no factor loadings, how do you know that you're measuring what you think you're measuring?
The slopes are the factor loadings.
Okay.
Uh-huh.
Does that make sense?
There about 60 slides from now, there's a slide that shows you how I'm going to algebraically rearrange this thing, turn A into a factor loading.
Okay.
The slopes are a factor loading. They are. Even though it doesn't look like it, they are. Question, isn't that how the GRE works? Yeah, the GRE actually uses what's known as a 3-parameter model, where they have different slopes and they have different lower asymptotes. So where the item crosses, basically what the lowest possible probability would be expected to be for a theta of like negative infinity. Like where it asymptotes out is a third parameter that you can let differ. And I think the GRE uses the 3-parameter model in its calibration of items. And that one's a popular one in educational settings. Because if you have a multiple choice item, to the extent that some of the distractors are not as good, it gets it easier to guess the right answer. So that's another way these curves can differ. Okay, go ahead.
My other question is if we're going to treat the slopes here as a factor loading, that means you can only have one factor, right?
In the world of IRT, they would say yes. In the world of no, IRT is just a factor analysis. Sure, you can have more than one slope, or more than one factor.
That doesn't even make sense then if you can't have the same, or if you have to have the same slope throughout.
You can have two factors being measured simultaneously. Like you could have a math theta, like math is sort of the higher order construct, but then you have like an addition theta and a subtraction theta. You could have
Okay.
that, and each item could measure. Usually, it only measures one thing in a confirmatory model. Multidimensional IRT models are often exploratory models, from what I understand. All the items load on everything, and that has the same problems as why I hate regular flavor EFA. But yeah, you can have multiple factors. It turns out that the estimation for these things with more than one factor is a giant pain in the ass. There's more slides on that too, but that's the short answer, that it requires numeric integration, which takes a lot more time and resources. So practically speaking, like when you say an IRT model, you're thinking of one trait, but it doesn't have to be that way.
The way you described it made me think of like, domains and factors in domains. So if you were going to consider like addition and subtraction as domains of the factor of math.
Mm-hmm.
So is that a good way to conceptualize that?
Yes, it is.
Okay.
And spoiler alert, you already know how to demonstrate whether or not one factor fits not worse than two. Likelihood ratio test. Are the heights comparable? Same on here. The catch is that the way that height is defined in these models is using a Bernoulli distribution as the basis for height rather than multivariate normal. It's a conditional distribution that says item responses are supposed to be independent after you control for all the factors. But otherwise, it's still the idea of height and comparing heights. So yeah. So what would happen to our funny little model if we let these slopes be different? Ta-da! Let's play Where's Waldo? What makes the new 2PL model different? Yes, AI. It is not artificial intelligence. It is individually varying discriminations. So the 2-parameter model starts with each item gets its own difficulty location and adds each item gets its own slope. So A is known as item discrimination explicitly. It is the slope at the location of the item's difficulty. In other words, let me get a picture here. Here on slide 33, the pinkish items have the same difficulty. The point where it looks like 0, my line's moved over, that's weird. The point where it crosses 0 is the same, but the lighter pink item has a steeper slope. So this would be allowed in a 2-parameter model where each item gets its own separately estimated slope. And the A parameter is the slope at the 50-50 mark. So the slope that is tangent to the curve at that point. Because as you can see from the curves, the slope changes. The slope shuts off. It gets shallower and shallower as you move up or down. So A specifically refers to the 50-50 slope at that point. So the two blue items, for instance, on this slide here, both are targeting the same level of difficulty. For both of these items, they have a difficulty value of -1, meaning somebody with a trait value of -1 has a 50-50 shot at getting them right. But between those two, The second item here has a steeper slope, meaning it's more related to the trait, meaning there's a steeper increase in the probability of getting a 1 as the trait increases. And so this is a 2-parameter model. And this is going to be directly analogous to the CFA models that we've just learned, because each item gets a difficulty and each item gets a discrimination. It's just that we literally use those words to describe what B and A are, rather than loading and intercept. What's going to happen is that these A slopes are going to be the same thing as factor loadings exactly, and B is going to be related to the intercepts, but they're not the same. But there's a one-to-one transformation to get back and forth. All right, what did I skip? Oh yeah, I'd already talked about this. So why Roche people think that this is voodoo? If we look at the ordering of which of these items is more or less difficult, the blue items are easier than the pink items because they have a lower difficulty value. But that ordering changes as you move up the trait. So if you allow each item to have a different slope, the slopes are eventually going to cross. So if we look at, say, a trait level of 2, look at the ordering of these probability curves. Now the pink item is easier than the blue item. So the fact that difficulty is not invariant to where you are on the trait, that is unacceptable to some people. That's a loss of specific objectivity, as it is called. To me, that's just a consequence of varying slopes. All right, so we talked about this a little bit. What goes into theta? If you have a Roche model where each item gets a difficulty that's different as a fixed effect, but all of the slopes are constrained equal, then all you need to know is the number correct to know theta. It's a sufficient statistic. Whereas if you have slopes that differ across items, to know someone's theta, you would have to know which items they got correct, not just which ones. Some items count more. The items that are more discriminating count more towards what your trait is predicted to be. So it's a different animal when you let the slopes differ. But I think if they fit the data better, then that makes more sense doing that. Can I give an example, like a real life trait in items that would switch up like this based on the trait level? It's hard to do so because I think of these curves crossing as just a natural consequence of the fact that they are not equal. But what is important about this is where the item is situated. So do you guys remember the idea of alpha and omega as like one number, right? Like reliability is constant. I'm getting to this later, but just to foreshadow, the reason that is the case is because in CFA, the slopes are linear. They go on and on forever. So if an item is good, it is good for a high person and a low person. But that's not the case anymore in this world here. So if I am trying to measure somebody who is super high in the trait, so let's think of this in the context of an adaptive test where I don't want to waste people's time. I have somebody who's doing well on all the items, and so I want to make sure that I can hone in on exactly how smart they are. Let's do this in an achievement context. Would I give them the blue items? Somebody who's out here at a theta of 2 or 3? No. Basically, all of these items would have very little information about just how smart someone is because the probabilities are all pretty much the same at this range. The blue items are designed to pick apart people who are in the range where the items are. The blue items are designed to measure people in the trait range of about -1, maybe -2 to 0, somewhere in there. The pink items are designed to measure somewhere between -1 and 1. So the fact that the items lose their ordering when you get out here to a trait level that they weren't intended for, to me is kind of like, so what? Like, that's not what those items are for. But it does bring up one of the biggest differences in how we think about items in this context. And it's not just, is the item good, but for whom is it good? So the blue items are not good for people with high trait levels. They don't discriminate people out here. Neither do the pink items for that matter. The pink items are better at discriminating medium people than the blue items are. But in order to have a test that measures everyone accurately, you need items all the way down the line to discriminate people at each possible level of the trait. So it's not enough to know if the item has a good slope, but you need to know where the slope is good. So a long answer to a short question. But other thoughts, questions? Oh yeah, 3 and 4 is next.
I feel like that kind of reiterates what you were talking about before, where in the Roche model, they only want one uniform slope. Well, in that case, you're not really discriminating between a variety of people at different levels of ability. You're only picking apart people at one ability level. And in theory, you don't even know where they are on that ability level, right? Because you're not really taking, well, no, you would, because there's an ability parameter.
Yeah, so this is, I'll go back to this picture. This is the Roche picture. You're not assuming that all items have the same difficulty. Items still get their own location.
Mhm.
It's that at that location, all of the items are equally good.
Okay.
Like at its location, they all work equally well. So this picture right here would similarly not do a good job at discriminating anybody at a
Yeah.
trait of 2 or 3. But that's not what those items are for.
Mhm.
So it's not necessarily like it's a limitation of the idea, but it's you need to have items out that far if you want to measure people out that far. And of 2 items that are at the same point of difficulty, you want items with stronger slopes because they do a better job at that point. Okay. Other questions, thoughts? So allowing each item to get its own slope for discrimination in addition to its own difficulty for location is the 2-parameter model. Here's 3. We pick up the letter C. So another way that items can potentially differ from each other, and this is unique to binary items, by the way, you don't see this in models for ordinal data, is a lower asymptote, which is traditionally referred to as a guessing parameter. So it is the probability of getting an item right sort of for the lowest ability person in the history of the world. Like if you don't even have any of the trait, what's the probability you get the item right? So if you have a multiple choice test, you can think of it as a baseline of like 0.25. If you have 4 options, for instance, if you have 5 options, it's a baseline of 0.2. But if one of your options is a really bad distractor, that probability of a random correct response goes up. And so you may have some items that don't asymptote all the way down to 0. They asymptote at a higher probability than 0. And you can estimate differences between items in what that lower asymptote is. And this is what the GRE uses, to the best of my knowledge. So the way that it works is that C is a lower asymptote to where you can like everything past the plus sign is gone. C is not a function of theta. C is just like the lowest possible probability that this item could have as a constant. C for constant. From there, the range between wherever C is up to 1 is then a function of the item's location, discrimination, and the theta of the subject. So the rest of the model only controls the difference between the lower asymptote up to 1. And it takes a lot of people to estimate this model. In particular, you'd have to have enough low ability people to be able to get a good handle on just how low C should be. So C sub I, in theory, it's possible to have items share a C parameter, but I've never actually seen that. But each item getting its own lower asymptote. And so then we'd have curves that look something like this, where, for instance, the two blue lines down here, they differ in their C parameter. So the lighter blue asymptotes at about 0.2, like that's where it would eventually level out, whereas the darker blue goes all the way down to 0. And as a consequence of that shift in the y-axis, the difficulty values don't have the same interpretation. They're not exactly where the 50-50 mark is, but you can still think of them as locations because they control sort of where the curve is on the x-axis. All right, and one more, D. So folks who've seen IRT before, have you seen D before? Is that a thing? Maybe? No, not a thing? Okay, I gave you something new then. So the 4-parameter model has a D, because why wouldn't it? We've already had A, B, and C. Of course the next one is going to be D. D is an upper asymptote. So it controls where the curve shuts off on the top. And the idea is that you can think of this as either carelessness, like you're not guaranteed to get it right no matter how high your theta is because there's some human element, or you can think of it as people wising up to the test. So let's say that you're trying to measure a trait, something like psychopathy, and you have an item that's like, I plan to go and kill someone tomorrow. Yes or no? Well, a psychopath, someone who's high on psychopathy, would say, yes, I'll check that. That sounds like fun. Somebody who is a smart psychopath might recognize that saying yes would result in some sort of legal action that is undesirable for my psychopathy. So they might say no because they know better. So there's all sorts of reasons in practice why the probability of a 1 might not be all the way at the top of the scale. It might be less than 1 for various reasons, and D is designed to capture that upper asymptote that doesn't get all the way to 1. M plus in the most recent iterations can estimate all of these models now. This is a new thing. I have not played with it too much because I don't have data to play with it, but this would be fun to play with since it's a less common model. So for those of you who have binary data, this might be something that you can play with if you have a large enough sample size, because you'd have to have enough super high people to nail down where the upper asymptote is, and you'd have to have enough low people to nail down where the lower asymptote is. Is that true about antisocial or criminal behavior more generally? Is that a way to consider underreporting? Yeah, I think so. There's certain items that people are not going to endorse or that they might not get right for reasons that have nothing to do with the trait. So a D parameter as an upper asymptote just allows that to be the case for some items. Um, so yeah. So the models that have these C and D upper and lower asymptotes, they do not have a direct factor analytic version. It's just the 2PL that has the A and the B. That is actually factor analysis in disguise. And I will prove it to you next week, or maybe the week after that. All right, that's a good place to stop. So questions? So we are fitting latent trait models still that allow items to differ from each other in their difficulty and discrimination, persons to differ from each other in their latent trait. We're just doing it with a very different set of notation at the moment, but this is still factor analysis, just predicting logits or probits, I promise you. And is anyone wondering how hard this is going to be to do in M+? Is anyone thinking that? Thank you for being honest if you're thinking that. I have good news for you. What if I told you it was one more line of code? I shit you not. One more line. In the variable section, you say categorical R, and you put your items there. That's it. And it figures out how many categories you have and estimates the right version of the model. Now, if you want to have C's and D's, that's a few more lines of code relative to the factor model. But if you just want to do a regular factor model type thing where each item gets a loading and a location type thing, just like we did for CFA, that's one more line of code. Hooray. So don't be afraid. Stay tuned. All right, then. We're out of time, so we will call it a day. Homework 3 is due Monday night. Let me know if you have any questions. Office hours start now. Otherwise, I'll see you guys next week. Peace out. Stay safe.